Good morning, everyone. I would like to begin by thanking the conference organizers for this wonderful workshop and for this invitation to speak. It's really a privilege to kind of speak here. Uh, Today, I kind of just want to kind of explain about our recent work on how MIP formulations turn out to be a very convenient and a powerful tool for when we try to perform counterfactual inference. We don't have data on something, but we want to kind of like perform inference on that. If we are trying to do the counterfactual inference, how particularly in the set of consumer choice, how does MEP formulations become very helpful and very powerful? That's what the focus of the talk today is. Without further ado, let me just kind of like start with this is joint work with my colleague Karthyek at SUTD and then our PhD students. So consumer choice. So we are like looking at like modeling consumer choice. We have a bunch of products. Let's say this is the universe of available products, uninspiring choice, but let's bear with it. So you have a bunch of consumer products, and let's say because of some retail space limitation, or because we cannot process too many items at the same time. Let's say the retailer kind of offers only this set, right? And then he kind of has a past history data of like how often consumers pick this one or this one or this one. So we have 10% of the customers in the past have picked the blue one, 20% have picked the green one. We have this market share data. Often what may happen is like sometimes I may have, as a retailer, I may have shown a different assortment, and I may have data for those different assortments as well. And now I want to know, if I have a bunch of products in my universe, which product should I show to maximize my market share or to maximize my revenue? So I am kind of looking at creating new assortments which may maximize my market share or which may maximize my the revenue. So I don't want to work just with these assortments. I want to be able to show new assortments. I want to show new assortments which may be profitable. We are talking about new assortments here, and that's where counterfactual starts coming in, right? Okay. So what is given? A given data set typically is observed choice data or market share, which kind of have been observed, observed in the past over different offer sets or assortments. For example, this is one offer set or an assortment of products, and this is another offer set or another assortment of products, right? The applications are not just in any consumer choice setting. It can be used, and often it finds use in transportation systems as well, where consumers kind of choose which mode of transportation to take, and consumer choice is a very powerful modeling tool. And abstracting the setup, we have a typical choice data given like this. We have a bunch of alternatives or products, and then we have various offer sets, various combinations of the products. And we have the market shares or the probabilities. Basically, given this assortment, how often product 1 has been chosen. Given this assortment, how often product N has been chosen. We have this data. The X marks that product 2 is not in this offer set, right? Okay. So we have an abstract, this setting can be abstracted into an abstract data set like this. And choice modeling is kind of talking about, hey, you give me any assortment and you give me any product, I want to know what is the probability of picking that alternative or picking that product within that offer set, within that assortment. So given any assortment S and given a product choice I within the S, how often consumers end up choosing I from S? That's what is this notation PIS is. Naturally, you see, if you are trying to specify a choice model, you are trying to say, hey, what is this PIS number for every possible assortment and for every possible product within that assortment. So it's inherently a very high dimensional. There are 2 power n assortments. If there are n products, there are 2 power n assortments, and this is inherently a high dimensional object, right? So how do we kind of given limited data, how do we inform this high dimensional object? It's a difficult task. It's an ill-specified task. So we often need a hypothesis. We need to say, hey, I'm going to work with this model class. The simplest of such model class is the so-called multinomial logic model, which is just saying, hey, each product has a utility, and the probability of choosing a product I is proportional to the exponential of that utility, and that's all. That's the simplest possible choice model. It's a parametric model. So once you kind of know the utilities of the products, once you have inferred the utilities of the products from data, we just have the whole choice model specified and we are done. But this is too simple to kind of like, this is too simple a choice model to kind of be representative of the myriad effects that we observe in the data. So we naturally there is a sense for looking for a more expressive or more representative choice models, and a lot of study has gone into this for the last 50 years in economics, operations research, and computer science, and many disciplines. Okay, so what is the use of choice model? Hey, okay, I have a choice model. What am I going to do with it? First, what purpose it serves is like it kind of explains the observed choices. If I have a choice model, I can explain the observed choices. Next, you give me a new, this is the focus of this talk. If you give me a new assortment A, which is not observed in the data. When I say assortment, this offer set is containing products which have not been offered before in the data, right? You give me a new offer set. I need to be able to impute how many fraction of the customers are going to choose product 1, how many fraction of the customers are going to choose product 2, and so on, right? So that is one of the fundamental tasks. You want to make predictions for new assortments which are not seen in the data set. That's one common use of choice models. And then once you have this ability, naturally we can ask more questions such as, hey, can you kind of find out an assortment which is of size, 10, but it kind of maximizes the market share. Or you can ask, hey, can you find an assortment which kind of like maximizes my revenue. So these are conceivable applications of choice models. And the simplest of the choice model, as I mentioned earlier, is this multinomial logit. And there has been a lot of work. Also, like a lot of people in the room also have looked at, like, developing more expressive choice models than the multinomial logic choice. And one very common canonical way of approaching choice is via this random utility perspective. So how do I go from developing from this simple model, multinomial logic choice, to developing a little more complex set of models? So that's where this so-called random utility model comes into picture, and it is 50 years old perhaps. So it's a classic idea. Here we have the universe of products 1 to n, and each product has a utility. Naturally, like, customers, not all customers perceive same products to be of same utility. So there is, like, there is a base utility for each product, and there is a random perturbation to it, random component to it. So there is a deterministic part to the utilities, and then the stochastic part to the utilities. And you want to see how often, like, how often a customer ends up, like, if a customer is going to be a utility maximizing customer. So an arriving customer is going to pick a product with the highest utility, but that is random, right? This is the random utility, base utility, which is deterministic, and then there is a random perturbation. The customer is going to pick the product with the highest utility. How often the product I turned out to be the highest utility product, that determines the market share. So this is the simple random utility model perspective of modeling consumer choice. And the parameters here would be the deterministic utilities and all the joint distribution of all the random vectors, random vector epsilon. So if I try to slightly generalize, like go from like, so this is one discrete choice setup that I talked about. We kind of like, or like this talk is only about discrete choice, but we want to extend this counterfactual inference machinery that we are developing here to slightly more complex settings where involved in probabilistic combinatorial optimization. Let me just explain the motivation here. So this is one setting where we are talking about consumer choice, and a related aligned setting we are going towards is this, like you are given a network. A customer kind of wants to go from a source to a sink, and they choose a path, a shortest path, let's say. How often an edge get picked in the shortest path could be a question, and we want to know that determines the traffic in that edge. Now, if I add a couple of new edges in that graph, how would the traffic change? Right? This is what I call as counterfactual inference. I have data given for the old network, but now I have added a couple of new edges. I don't have data for this network. I really don't have any data for this network, or I'm in the process of designing, hey, whether to add edges here or whether to add edges in a different place. I have a budget to add 2 edges. Where should I add? Right? To answer this question, you need to know, if I add these 2 edges, how would the traffic change? That's counterfactual inference. And here, like, this machinery that we are developing here hopefully can also kind of, like, extend to this type of counterfactual inference setting. The commonality between choice and this setting is, like, in the choice, how often a product I gets picked is expressed as a utility maximization problem. Similarly, here, how often an edge gets picked is also written as a utility maximization problem, or a cost minimization problem, but perhaps a more combinatorially, like, kind of like challenging one. So, we can kind of extend this question on counterfactual inference to multiple settings, not only for the shortest path. You can also ask, hey, given a project activity network, if I change the workforce composition, what is the likelihood of a particular arc becoming critical? That is again a counterfactual inference question. So, or in a two-sided platform where customers are matched with suppliers. So, if the platform fee is raised by 2%, how would the matching rate be affected? So, these are questions. I call them counterfactual inference because you are talking about systems for which you haven't observed data. You have data for a slightly different system, but you want to kind of make inference for new models, new systems. Okay. So, the broader goal, as I kind of mentioned, is to, given limited data, develop predictions on counterfactuals not observed in data. In this talk, I will just perhaps like kind of limit myself majority to the choice and then move on to, if there is time, I will cover a couple of results on this network setting. Any questions at this stage? I haven't introduced the model yet, but like this is roughly the motivation. Okay. Now, back to discrete choice, back to consumer choice, the easiest and the well-defined setting where I have n products, I have random utilities for each product, there is a base deterministic utility and there is a random perturbation. We saw that the simplest model is this multinomial logit model. And another model on the complex, more complex end of the spectrum, this is the simplest of the possible models. Another model in the more complex end of the spectrum is this so-called random utility model, in which the probability of choosing a product I is just same as how often I maximizes, the product I maximizes this utility, right. So, this is the random utility model. So, these are two ends of the spectrum. In one end, what you have is a simple parametric model, which is tractable, which has considerably less representation power. It is not expressive at all, but it is useful for performing many downstream cost prediction tasks as well as optimization tasks. So, it is a very convenient model to work with, less representative, it has very little representative power, but it is a very tractable model. So, if you are using a very less representative model, then there is a high risk of like not capturing faithfully what the data is saying. So, there is a high risk of model misspecification. On the other hand, you have a very expressive model, which is the random utility model, which has a substantial rich representation power, right. But learning from data is similar to kind of like is kind of like known to be NP hard, and like it's a very hard problem to learn from data. It's intractable in general. It's tractable in some special cases, but largely intractable in general. The other extreme. Okay. Now in this talk, like so, we have these two extremes. One is parametric, and another is totally non-parametric, and it's just very expressive. One is tractable, and the other is very representative. The other is not tractable. So, can we balance representation power and tractability? This is the fundamental question that we are interested in. Can we develop choice models? Can we develop choice models where you kind of like are not losing much on representative power? You are not committing a lot of model misspecification. You are still having a representative model, but the resulting the resulting model is tractable and convenient to work with. So, trade-off between tractability and representation power is what we are examining here. Right. So, and we want to kind of like showcase this class of models called marginal distribution models as a very convenient choice in kind of like marrying tractability with representation power, and then also show how many of the complex prediction questions can kind of be written as compact mixed integer programs in this under this model. Yes. So, isn't MNL a special case of random utility? Yes, MNL is a special case of random utility model. Yes, that's correct. But this is still the comment that still applies, that this is very simple and that is richer. Being rich, it includes this as a special case. Thank you. Thanks for the comment. Yeah. When you say it is parametric, the parameters on the MLN is sorry, what is the parameter? The parameters are the utilities of the products. Yeah, the utilities of the products. If you have covariates, then the utilities can be written as a linear or a non-linear representation of the covariates, and you will be learning those parameters. But the utilities are the parameters of interest here. Yes, it can be. Yes, thank you. Okay, now this is we want to marry trade-off with representative power, and we kind of like claim that this class of models is kind of helpful and conducive in doing this. So, I am going to introduce this class of models called marginal distribution models. Okay, so that's the next 5 minutes or so, or maybe a couple of minutes. So, I have this, we saw this random utility model. What is a random utility model? We are now fine with this perspective. We have this random utility model where the probability of choosing a product I from an assortment S is nothing but how often I maximizes the utility. So that is the random utility model. And the other type of way, so the two difficulties in general, what are the parameters here? The parameters here are like the utilities themselves and then the joint distribution of epsilon of the random errors. So if you have a simple case where the errors are IID Gumbel distribution, that is where you recover multinomial logit model as a special case. But as such, the model is specified by the utilities, the base utilities and the joint distribution of epsilon 1 to epsilon n. And this joint distribution you have to infer from limited data, and that is statistically always challenging, right? Like so, if epsilon 1 to epsilon is taken to be IID Gumbel, in that special case alone, we recover multinomial logit as a special case. But otherwise, it's not necessarily easy. So two difficulties which are associated with this random utility model are, one is this estimating of the joint distribution from data, and the other is like even if I have the joint distribution with me, how do I compute the choice probability? I'll have to do Monte Carlo computations. There is no closed form expression like what we had for multinomial logit. We will have to do some Monte Carlo simulation to find out what is the probability of choosing a product I from as an assortment S. So this is one set, random utility. And in economics, there is a kind of like a very different approach of like kind of looking at the same question, that is called as representative agent model. Okay. So in the representative agent model, if you kind of try to find the product which maximizes the deterministic utilities, it will always lead to a degenerate choice, right? Only one product with the highest utility will be picked. But to discourage that, instead to model stochastic choice, what they do is they add a convex penalty. This is a convex penalty, so this becomes a concave maximization problem, right? So here you kind of think of a representative customer as someone who performs this, who solves this convex optimization problem to get his or her choice probabilities. So this is what is called as the representative agent or representative consumer model in economics. And once I kind of like take this solution, I kind of like can find the probability of choosing product I from an assortment S by looking at this vector. This vector contains all those numbers. I can take that number that I want from this vector. So in short, in representative agent model, I don't need to go through this route of Monte Carlo simulations and so on. I can just inform what my choice probabilities are by solving a convex optimization problem. And it has been shown that this is a bigger class than random utility models. So it's a very expressive class because the degrees of freedom here, the parameters you have here are the deterministic utilities as well as any convex function you can use as penalty. So naturally, what is the challenge with representative consumer model? You have choice probabilities. The advantage is that it is a convex optimization problem. You can compute choice probabilities by solving a convex problem. But the limitation is that inferring the penalty function C from data is challenging. That can be hard. So these are the two approaches, and we can arrive at marginal distribution model from either of these approaches. Let me go with the first one. So the objective here is for me to introduce what is MDM or marginal distribution model in the first place. And MDM is nothing but if this penalty function, if you take it to be a separable function, that's all is marginal distribution model. So what is happening is because of the separability, each of the component is marginally optimized, and so that's the marginal distribution model explanation. So if you take if you say, hey, the set of all convex functions which can be used as penalty is crazy, I cannot inform from data. Let me be very realistic. I'm going to assume it is separable. If I assume it is separable, that is marginal distribution model, the easiest starting point. Okay. If you want to arrive at marginal distributions from random utility perspective, that is also possible. That's what I'm going to do next. If you are fine with either perspective, it's okay. You don't need to be fine with both. But there is a duality here. So I'm going to now arrive at marginal distribution model from a random utility perspective. So here, there is a deterministic utility and there is a stochastic part to it, of which I assume the marginal distributions are given, but the joint distribution is not specified, because informing joint distribution is what is hard from data. I assume marginals are given and I say, hey, I'm going to do the same thing as random utility does, which is how often I maximizes the utility. Product I maximizes the utility, I'm going to do the same thing, but I'm going to compute that with respect to the joint distribution, which maximizes a certain expectation, which maximizes this utility expectation. So I'm going to let this problem determine what the joint distribution should be. And so this is a special extremal distribution with which respect I kind of like compute the choice probabilities, and that becomes the marginal distribution model. And there is a clean duality result which says, hey, if you take this random utility perspective, what you end up with is, separable utility is what you end up with. So, the convex penalty, the separable convex penalty can be written in terms of the marginal distributions that you started with, and that is a well known duality result in the literature now. Okay. So, we can arrive at marginal distribution models from either perspectives, and this is how I like to kind of understand it. So, basically easily like speaking, there is this whole class of representative consumer models, of which MDM is a special case, where if you use separable penalty, you come with you are working with MDM. That's all it is. Okay. Now, so just as an overview, what is known in the literature is that, like, we have this RUM viewpoint of utility maximization viewpoint of marginal distribution models, and there is an equivalence with the representative consumer, which is what I kind of dealt with in the last slide. And then the computational advantage here is that, hey, for finding the choice probabilities given a model, I just need to kind of solve a simple convex optimization problem rather than a Monte Carlo simulation and so on. So, it's computationally advantageous. That's the selling point of this model. Okay. And you can recreate MNL as a special case, like how MNL is a special case of random utility. You can also recreate MNL as a special case if you use x log x, a special penalty function as a penalty. You can recreate MNL as a special case, and then this model kind of like at least under very restrictive assumptions have received a concrete axiomatic treatment in economics literature as well. And then in choice modeling per se, it has been shown to be conducive for certain assortment optimization tasks and pricing tasks under restrictive settings. This is known in the literature, and this marginal distribution model has also been kind of receiving like kind of like interest outside choice as well, in smooth optimal transport or in profit inequalities and in many other settings in computer science. We do see this marginal distribution model getting some tractability. So, this is a rough overview of where the literature is. Now, I am going to introduce our results. Okay. So, the first question is, hey, I have this model, but what is its representative power? There is a conjecture that, hey, it could be much more representative than parametric models, but how representative how expressive it is, how rich it is, that is the first question, and even this is not known. So, the question that we are asking here a little more precisely is, for every given, you give me any assortment collection, you give me a bunch of assortment collection, offer sets collection. The question that we are asking is, can we characterize the set of all MDM representable choice probabilities? I do not say this is the penalty function. Can you represent the set of all MDM choice probabilities? That is the first question. So, in other words, if you give me choice data, what are the necessary conditions for that choice data to belong to MDM? That is the first question that we are asking. Okay. So, basically, can we have a clean, precise characterization of what is the representative power of this model? Why are we asking this question? Because such a question has been like kind of like asked for RUM for 50 years in economics and operations research, and it has received a like this has helped us understand the model better and also develop very efficient algorithms. So, so for RUM, the counterpart results have been around like since 1960, and then an equivalent to learning an RUM is equivalent to learning a probability distribution of the space of rankings. That is also not known, and this type of characterizations have kind of triggered an enormous kind of like has had a lot of implications for algorithms. A lot of nice algorithms have been developed. So, we want to kind of like, so what has been done for RUM? We are initiating the study here for the analog MDM. Okay. For RUM, it has been done, but it's hard. It's computationally hard all the time. So, can we kind of have better hope with MDM? So, recall that MDM is kind of derived from RUM as well as RAM as a special case, right? It's okay. Anyway, the first result is, we say a probability. So, we do actually pin down precisely the necessary and sufficient conditions for choice probabilities to be represented by MDM. So, we say, hey, given set of choice probability vectors is representable by MDM if and only if there exists a ranking over the assortments. Okay, if there exists a ranking over assortments which agrees, which is consistent with what the probabilities are saying. So, if PIS is less than PIT, where S is one assortment and T is another assortment and I is a common product to both the assortments, then lambda S should always be greater than lambda T. So, I will come to how this happens, but as long as the order is maintained, as long as there is an ordering on assortments which is consistent with the data, it is representable by MDM. So, just to even before going into the details, let me just introduce a couple of examples. So, this is a setup where across products there is a consistent ordering across assortments, and that order can be mirrored in the negative of lambdas as well. Okay. This is an example where the data can be represented by MDM. Are different, then it is not representable by MDM. That's all. So this is an example, exactly the example that you're asking, where you have two common products between S and T, but the order, like the probability of like choosing, so you see the order is kind of like reversed, in which case it is not representable by MDM. Yes.
If the vector P is say submodular, is there any submodularity in any way?
So submodularity, interestingly, is at least like we are finding that like the total market share is a submodular function, and there are certain interesting things we are finding, but at the moment we haven't had made a large headway with submodularity. Thanks for the question. Yeah. Yeah, random utility can do it. Random utility can do it. So it is a little restrict. Okay, we will see how random utility and MDM compare. One is not a subset of other. Okay, so if your choice data has this feature, then it cannot be exactly represented by MDM, and that's what it is. That's the limitation of the model. But if it kind of has this agreement, which many regular models do, like then you have this agreement. And MNL, nested logic, all kind of at times belong as all belong to MDM, right? Okay, so it is more representative in certain ways and less representative in certain ways, which I will come to, but this is the precise characterization. And if my data has this property, I have it, otherwise I don't have it. Yeah. If that is a limitation, RUM can represent it. I do agree with you. Yes. Markov chain, I think, will be more representative in this setup. Yes, Markov chain choice model can, I think, model the other way. Yeah, it is more, it is in that sense, it's more representative. Okay. So this is the example. Hopefully the example gave a sense of like, when the data can be represented by MDM and when not, right? Okay. So why does this happen? If you just are a little curious, then we have that, then I have a proof, but in any case, the point is like, then I'll have a picture proof next. But in any case, important points first, this characterization, if you see whether choice data belongs to MDM, this condition is verifiable in polynomial time. It's very simple. It's verifiable in polynomial time. And then what we see, the distinction between RUM and MDM, they are very different in one sense. RUM like kind of looks at finding a probability distribution over the space of rankings on the products. On the other hand, MDM is talking about finding a ranking on the observed collection of assortments. So they are very different models to begin with. So this understanding we didn't have before, but we have it now. One is NP hard to verify consistency, and the other is like polynomial time. And why does this happen? To kind of see that, here I have the utility maximization problem that I talked about. This is the utility maximization problem I solve to find the choice probabilities. This we saw before. If I write down the KKT conditions, this is how the KKT conditions look like. Now if I kind of like look at the same for another assortment T, the Lagrange multiplier with the respective Lagrange multiplier lambda T here and lambda S here, that also satisfies another KKT condition. If PIS is less than PIT, then because of the monotonicity of the marginal distributions, that should be reflected in lambda S and lambda T, and that is why we are having this ordering. So if you want to see it pictorially, so here I have lambda T and lambda S in the x-axis and PIS and PIT in the y-axis, and if there is an ordering of PIS and PIT, that should be reflected in the lambdas, and this is why this is coming. This is one direction. The other direction is, as long as the ordering is consistent, I can always construct a marginal distribution like this. That is the reverse direction. So the proof is quite intuitive, not too difficult. It comes just from the KKT conditions. Okay, and this we saw. This is an example where the data can be represented by MDM, and this is an example where the data cannot be represented by MDM. We saw this, and now coming to Vinit's question, hey, how representative this is, like how rich this is. This looks a little like a limitation, how rich this is. What we do find is, both MDM and RUM consist of like, simple models like multinomial, nested logic, etc. as special case, and then it is easy to create small instances where the data is represented by RUM but not MDM, like what Vinit pointed out. The other side is, it is also easy to create instances, simple instances, where the data can be represented by MDM and not by RUM, right? So either way is possible. And what we also see is, compared to parametric model classes, what we see is this MDM class has a positive measure. Like if I look at the space of all choice probabilities which are represented in the space of all choice probabilities, what happens is this parametric models like MNL and nested logic, they have zero measure, they are very sparse. But on the other hand, MDM has positive measure, RUM of course will have positive measure too. So it's much more representative than the simpler parametric models. And then yeah, there are other advantages which are not too important to dwell at this point of time. Any questions? This is the representative power and this is the main result. Now I will go into applications of this result. Any question at this point? That it can capture, that is not a problem. That it can capture, yes, that it can capture, yeah. Okay, the first application we are going to look at is, hey, I have this characterization. So how useful it is going to be for counterfactual prediction, right? Like, so I have a bunch data on a bunch of assortments. Now you give me a new assortment and you want to say, hey, how the choice probabilities for this new assortment will look like. And the simplest thing that what we can say is we cannot pin it down because it's an ill-specified problem. We cannot pin it down exactly, it's not identifiable exactly, but what is possible is you can develop easily see because of the characterization, you can easily put constraints on what all the constraints the probability should satisfy. See, this ordering is already, this ordering between the Lagrange multipliers are already satisfied by the data. So my new assortment should satisfy these ordering. So my new probability should satisfy the resulting ordering. So you can easily develop constraints on the on what all choice probabilities, what all constraints this unseen assortment choice probability should satisfy. So that will look simply like this, right? So the ordering in the Lagrange multiplier should be preserved. And if you want to make counterfactual inference, you are just asking, hey, does there exist a ranking and a set of choice probability variables? The blue ones are the variables which satisfies the ordering that I showed before. You can write it as constraints. So if you have the data, the p's are not variables, but if you don't have data, yeah, the x's are variables. So, but you can easily develop constraints on the choice probabilities for the counterfactual assortments. So this springs out immediately from the characterization I showed before, nothing new. These constraints can be written immediately from the characterization I showed before. And then as you see, these are not immediately like kind of like these are not immediately handleable, but I can always kind of use a binary variable to say, hey, what is the ordering between lambda a and lambda s? If once I use the binary variables, then I do get a mixed integer representation for the polytope representing the choice probabilities for the unseen assortment, right? So for this characterization becomes easy to handle as integer with the integer variables. Now I have this space of all possible choice probabilities for the unseen assortment. Now what do? I cannot pin it down. One can use robust optimization, which you can say like how Veg Farias and Shrikant did it for RUM. You can say, hey, this is all the set of probabilities that can happen. What is the worst case revenue and what is the best case revenue? And this can be written down. This in one sense, you are not making any more parametric assumptions. You are just allowing the data to speak for what the revenue should be. You cannot get an exact estimate, but you can get a range. So basically, you can get if you do the inf of it and if you do the sup of it, you get a range for what is the range in which my revenues will lie, right? So this is possible because of the characterization that I showed before. And generally, we can write it as a compact mixed integer linear program. But in the case of structured assortments such as nested laminar cases, you do have a polynomial time algorithm. You don't need the mixed integer programs. You do have a polynomial time algorithm. So this is one application. So this is possible. Finding the worst and the best possible predictions for revenues and choice probabilities is possible because of the characterization that I showed before. The second application is to kind of like see, hey, is this model even a good model? Is it how representative it is? And then to find the best fit, that's what I call as best fit. So you are given a data, obviously as Vinit was saying, this is not going to satisfy all the, it's not going to have the exact signages that we required. So it's not going to be exactly consistent. So even if you have a data which is not consistent, how close or the sign inconsistency can also happen because of noise in the observed data. So how close is it to my MDM feasible region, you can ask. This is the set of all choice probabilities that my MDM model can represent. How close is the observed data to this model? That can also be written as a compact mixed integer linear program. And this is similar to the limit of rationality notion which was proposed by Shrikant and Parth in their 2019 limit of rationality paper. So, the limit and the best fit can be evaluated by a compact mixed integer linear program generally, and in some cases like nested laminar structures where if your assortment offer sets are nested and laminar in structure, there can be a polynomial time algorithm. I didn't go into the details, but roughly these are the two ways. Like the characterization allows you to kind of like start doing these things non-parametrically. And finally, some empirical validation. So this is case study with JD.com dataset. So here you have a bunch of products and assortments which is given as before. What model should be used to prescribe the demand? We compare comprehensively empirically with both parametric and non-parametric models. So what we see here, what we quantify here is like which model explains the data best, and the models that we are considering here are multinomial logit, Markov chain choice model, latent class MNL with 10 classes, and then RUM and then MDM. So these are the different like very popular choice models which are available now, and we are benchmarking them with MDM. And what we do see is RUM and MDM. RUM has very rich representation, and it's going to very well. It's going to have the lowest losses. So RUM is orange, and it has the lowest losses every time. But what we do see is MDM is competitive. It kind of offers a much better fit compared to the other parametric models that we have studied, right? And the second is if you look at the computational time, the picture inverts. So RUM is computationally extremely expensive. Like so, RUM orange is extremely expensive. Latent class MNL is also expensive, and what we do see is like Markov chain choice model is quite efficient, and then like also like RUM is quite efficient in terms of computation. So overall, if we synthesize the findings in the two pictures, what we do see is, at least in this real world data set, what we do see is MDM has much smaller loss, okay, than the parametric models, but while being significantly faster in computation than the non-parametric RUM. So it is kind of like the premise that we started with was, hey, can we have a rich representation power while being tractable, and we are kind of seeing that at least manifest in the experiments. And the second is like, hey, how good are you doing on new assortments, counterfactual predictions on new assortments? I have this data, but I want to make predictions for several new assortments that I have not seen in the data. How good are you doing? Can you ask, when you ask that, how I am going to kind of like my task is to basically, if you give me A, B, C, 3 assortments, I want to kind of rank them in the order of revenues. That's a measure of prescription, like how they kind of perform in the order of their revenues. I want to do this. So I want to rank the unseen assortments in terms of their revenues. And to measure the quality of ranking, we use this so-called Kendall-Tau distance, which is a natural measure for like how many pairwise swaps you have to go from one ranking to other ranking. That is what is Kendall-Tau distance. For example, if ABC is the predicted ranking and BAC is the ground truth ranking, then the Kendall-Tau distance will be 1, because you can do just with one swap, you can go from one ranking to the other. So this is the metric that we use, and we do see in several instances, in several data sets, and these are all data sets filtered from the real world JD.com data set. What we do see is MDM again performs reasonably well, MCCM performs reasonably well on counterfactual prediction, and then RUM surprisingly is not so good. Despite being very rich also can hurt you, because there are too many degrees of freedom. So the bounds are like the worst case and the best case bounds for RUM are very wide, and RUM surprisingly doesn't perform as well. Again, we do here see that MDM performs better than RUM, and of course MNL is not expressive at all. So MDM performs better than RUM and MNL, but it has competitive performance to richer parametric models such as MCCM, Markov chain choice model, and latent class MNL. And then for broader counterfactual inference, I do have a couple of characterizations. Similar characterizations one can derive based on the Lagrange multipliers, but I am not going to bore you, like, because we are also short on time. In short, like choice model setup is a simpler problem in one sense, because the combinatorial explosion doesn't happen. On the other hand, in a network setting, like a combinatorial explosion can happen, but even in this case, it is conceivable, it is possible to write the representable conditions for MDM in a polynomial time manner. So that is doable. That is the punchline here. In any case, let me just go and conclude in the interest of time. So in this work, we kind of like presented the first exact characterization for the MDM class of choice models. And using that characterization, we developed the non-parametric estimation and prediction approaches. And then we demonstrated superior numerical performance, and these results kind of like lend themselves naturally to performing counterfactual inference on broader probabilistic combinatorial settings. So with this, I conclude the talk, and thanks for the opportunity and thanks for listening. I'm happy to take questions.